So earlier in the video, I said that I claimed that the Cartesian coordinate system and the complex plane are one and the same thing. So the complex plane is a Cartesian coordinate system, and not only that, it is the Cartesian coordinate system. Okay, so I'm going to explain this in a little bit more detail just to make it perfectly clear. Okay, so here is a Cartesian coordinate system. This has positive x to the right, and this has positive y pointing up. Okay, here we have x on the forward diagonal, which is an indication that x is real. Okay, so all you have to do is look at the forward diagonal to see which axis is real, and the backward diagonal is the imaginary component. And then we have the rotation matrix here. So this matrix without the cosines can be thought of as a translation matrix. Okay, these are used in computer science all the time. When you add two matrices together, I know some people want me to use the word vector, but I'm not going to use the word vector. When you add these two matrices together, you get a translation. Okay, so when it's a point, sometimes I call it a point. When I refer to it as a point, it means that I'm measuring from the origin, which is 0, 0. Okay, so this is x to here and y to here. Now, the reason I put the negative y here is because this matrix also contains the negative solution. Okay, so this contains positive x, positive y, and positive x and negative y. And so both solutions are in this matrix here, which may seem redundant. And sometimes it is redundant, and sometimes it is not redundant. Sometimes it's actually very useful to have both solutions in the matrix. You definitely, when you're using this matrix as a transformation matrix, you have to put everything in here. You can't, you must put everything into this matrix in order to get a proper transformation. Okay, so this is important. You can't just have cos theta, I sine theta. You kind of need the whole matrix to do the transformation. So what I'm going to do here is I'm going to first, I want to show you the arbitrariness of choosing x for the horizontal and y for the vertical, or horizontal for real and vertical for imaginary. Okay, I would prefer to have it this way. Okay, I would prefer to have positive y pointing to the right and positive x pointing down. Basically, all I did was I rotated the coordinate system exactly 90 degrees so that positive x points down and positive y points to the right. The other way you could look at this is I rotated the camera counterclockwise so that I'm looking at it in a different orientation. So nothing changes except that now the vertical axis is real and the horizontal axis is imaginary. Now, why the heck would I want to do something like that? Okay, the reason I would want to do that is because now the coordinate system matches the Mandelbrot set. Okay, so here is a beautiful painting that my friend Gaetan Labelle did for me. He passed away from cancer a few years ago, and he did this huge giant painting for me for an art show called Vision of the Jewel Line Buddhaverse. And so I designed a painting where I had the a Buddha-like figure. This is Amateus, the giver of infinite life. Okay, and Amateus is an emanation of Adi Buddha, which is the giver of, or the bringer of infinite light. And so I thought it was appropriate to use this particular Buddha figure. Plus, it is this is the only Buddha figure that is exactly left-right symmetrical, like the Mandelbrot set. Okay, so this is the Mandelbrot set, the boundary out here, and in this orientation, I like it in this orientation because it looks like a seated Buddha. I always thought it looked like a seated Buddha even before I painted a Buddha in it. Okay, so I thought it was important to have the x-axis. This would be normally what we call the x-axis, the real axis, okay, pointing vertical, and the imaginary axis being horizontal. And so I didn't want to change the x and y's. I still wanted x to be real and y to be imaginary. If I switched x and y, it would have the same effect, but then that would confuse you as well. So I'm trying to do the least confusing thing. All I'm doing is rotating the coordinate system 90 degrees clockwise so that the Mandelbrot set is sitting in an upright orientation. And now I have a coordinate system that matches a figure that that I recognize, okay? And so if I recognize this figure, so here's another good reason to do this. I want you to imagine that the aliens come to our planet and they want to understand our math, okay? They want to understand our coordinate system. They want to understand our symbols. And I have to assume that, because the Mandelbrot set is so simple, okay, the equation to generate is so simple. All I need are these two matrices. Okay, actually, I just need this matrix here. So it is so simple that I'm quite sure that if aliens came to our planet, that they would have computers and that they would have seen this figure. Okay, so so if I show them this figure and I show them this figure, okay, they are going to know, I'm sure they have coordinate systems, they're going to know that we've got the real on the vertical axis, and that positive real is pointing in this direction, and they're going to know, they're going to learn a lot about our math just in our symbols just by looking at this figure. They're going to know that this means positive, they're going to know that this means positive, they're going to know that this means negative, they're going to know that this means negative, they're going to know that this, arrow, I'm sure they have arrows, is pointing to the positive. So it's quite possible that I would be able to communicate with them fairly easily using the Mandelbrot set as my standard, as my coordinate system, okay? So when you put when you put the real on the horizontal axis and the y on the vertical axis, what you end up with is the Mandelbrot set on its side, like this, okay? And so there is a symmetry in the Mandelbrot set, okay? There is a left-right symmetry, a mirror left-right symmetry, which is much harder to see when it's on its side. Yeah, I can see that it's symmetrical, but it's not mirror symmetrical because mirrors only do left-right symmetry. Mirrors do not do up-down symmetry. So that's another reason why I think it's important to put the real on the vertical and the imaginary on the horizontal, okay? And so that is what I'm going to stick with. This is going to be my coordinate system. This is going to be my standard, my convention, if you want to call it that. This is going to be my convention moving forward, okay? So I want to also show you the arbitrariness of the letters, okay? We always put, X on the horizontal and Y on the vertical, which is why when I do this, it is going to confuse people. And so I could just as easily call them A, B, C, D. Okay, so this might actually be more palatable in the sense that you don't have the association with the X, Y, and the Z in certain orientations. And so I'm going to put A on the vertical. A is the forward diagonal of the 2x2 matrix, and A is this axis, okay? And B is horizontal. B is the imaginary component, and so B is this way here. And now you can see the beautiful left-right symmetry, mirror image symmetry of the Mandelbrot set, and you can see the graph here. So this would actually be very easy to explain to an alien. They would get a lot of, I'm pretty sure that if they can draw lines and they can draw squares, that they would know that this is a 2x2 matrix, that they would know this already, and that they would get a lot more information. So they would see the positives and the negative signs, so they would know that those are the symbols we use for positive and negative, and they would see that the vertical is the real component and the horizontal is the imaginary component, which matches the orientation of the Mandelbrot set. So this would be a beautiful way to explain to someone that uses a different language than me, to explain to them what my convention is, okay? And you might recognize this as A plus BI, which you could, if you want to put the positive identity in there, it's A times positive 1 plus B times positive I. And so that this matrix is, this is the algebraic symbolic way of writing this 2 by 2 matrix. Okay, A plus BI, this might look familiar to you, you've probably seen that before, is literally this matrix. This matrix is under the hood of A plus BI. So now what we're going to do is we're going to square this matrix. And as you may know, to generate the Mandelbrot set, you use the formula Z equals Z squared plus C. So we're going to deal with the Z squared part because that's actually the hardest part, because in order to do Z squared, you need to do matrix multiplication. So what I'm going to do is I'm going to show you how to do matrix multiplication in order to do the Z squared part of this formula here. Okay, so I am using row convention to do my multiplication in this video. So in order to do row convention, in order to do matrix multiplication, what you do is you take the top row of the matrix on the left and you multiply it by the first column of the matrix on the right, and then you place that into the upper left quadrant of the final 2 by 2 matrix, okay? And so it's A times A plus, so then you add them together. So you go this one times this one plus this one times this one. Okay, so it's A times A plus B times B, or plus minus B times positive B. Okay, so that's easier to write actually. So I did it in reverse, but it doesn't matter because multiplication is commutative in complex numbers, in 2 by 2 numbers, okay? So this is equal to A times A plus minus B times minus B, okay, which simplifies to A squared minus B squared. Okay, so now we've done, we've calculated the first quadrant of the 2 by 2 matrix. So next we're going to multiply the first row by the second column of the matrix on the right. And so that would be A times B plus B times A. Okay, so that's pretty simple, and that simplifies to positive 2AB. Okay, so that's the first row is now complete. The answer is in the first row. Next, we take the second row and we multiply by the first column. So now we're taking the second row and the first column, which is minus B times A plus minus B times A plus A times minus B. Okay, and so that is equal to minus 2AB. So now you can see the backward diagonal is complete, and you can see that multiplying two complex numbers, two 2 by 2 matrices together, produces another 2 by 2 matrix where the you have the opposite sense on the backward diagonal. Well, I just want to say one thing. One person complained about me moving my mouse around too much in the video, and I do that. I apologize. I'll try not to do it, but it's just when I'm talking, I'm a little nervous, I guess, and I kind of move the mouse around. So hopefully that doesn't bother you too much. I don't know if I can stop doing it or not because it's become a habit. So hopefully you can forgive me for that. Okay. So, so we're done with the first 3 quadrants. Now we're going to do the 4th quadrant. So now we multiply the second row by the second column. So we've got minus B times positive B plus positive A times positive A, which is A squared minus B squared, which is the same as the first quadrant. So here you see now we have a nicely formed complex number, if you want to call it that, 2 by 2 matrix. It is a complex number. Complex numbers are 2-dimensional numbers that have, where the forward diagonal has the same values and the same sense, and the backwards diagonals has the same value but opposite sense, okay? So I think it's okay to call this a complex number. It is a number. These numbers work together. It is not 4 different numbers. It is there's got the same number here and you got the same number here, you have the same sense here and you have the opposite sense here. So this is how you square, okay, this is the formula you get, this is what you get when you square the 2x2 matrix. This A and B happens to just be a coordinate somewhere in the complex plane. It doesn't matter where. So the original A would be somewhere on the vertical. It would be in the what we're calling X, but now I'm calling A. Okay, so A, B might be over here, or it might be over here, or it might be over here. So the starting condition that we place into the Z equals Z squared plus C formula is going to be a coordinate in the complex plane. Okay, then when you square it, you get this value here. Now, if anyone's ever generated the Mandelbrot set algebraically, you will realize that this is the formula for the real component, and this is the formula for the imaginary component. So the matrix multiplication does the algebra for you. Okay, so you can see, obviously, this is in two entries of the final matrix, a squared minus b squared, and then 2ab, or minus 2ab. So the 2ab gets you the right-hand side of the Mandelbrot set, and the minus 2ab gets you the left-hand side of the Mandelbrot set, okay? Because the Mandelbrot set is symmetrical, mirror image symmetrical about the real axis, which is the vertical axis in this case. So in the code I gave you to generate the Mandelbrot set, I gave you a matrix multiply function. Okay, I gave you a function that does the matrix multiplication for you. So technically you don't need to know this, but I thought it was important that I go through the matrix multiplication table, the matrix multiplication procedure, just so you can know how it's done. It's really not that hard. You just have to remember the order of everything. And so first you do the first row, first column, then you do the first row, second column, and that gives you the upper right quadrant. Then you do the bottom row, left-hand column. Then you do the bottom row, right-hand column. Okay, so that is the order that you do things in case you need to do it by hand. If you're in a test or something and you don't have your matrix multiplication function handy in your calculator, then you might want to be able to do this by hand. Okay, so the next thing I want to just talk about briefly is the arbitrariness of the coordinate system itself. Okay, so I think it was maybe a little more palatable when I was using A and B, because you don't have the associations with X and Y and, you know, real and imaginary, okay? But I could just as easily have used X and Y in my discussion. I could have easily done everything. So A is X and B is Y. Okay, I could have just as easily have done that. Or I could just as easily have said real and imaginary, okay? So I could just use the letters R and I instead of X and Y instead of A and B. Okay, so the only thing that changes in the complex plane is the labeling of the axis. This is still a Cartesian coordinate system. I don't really need to invoke real and imaginary other than to compare the language with the standard language, okay? Real and imaginary. Real is on the forward diagonal, imaginary is on the backward diagonal. In my convention, my Mandelbrot set convention, real is on the vertical axis, positive real points down, imaginary is on the horizontal axis, and the imaginary component points to the right. And so this is the convention that I'm going to be using. In this convention, if there is a positive Z, so in a three-dimensional, if I want to put this into a three-dimensional coordinate system, positive Z would be pointing towards me. Okay, so when I'm using the 2x2 matrix to do rotations about different axes in a three-dimensional coordinate system, then positive Z is going to point towards me. But it is kind of standard to use XY. It's become standard to use XY in computer graphics, and so it's going to be very difficult to switch to using A and B, and so I'm just going to show you what it looks like when you use x, y. Okay, so you place the a's with x's and the b's with y's, in knowing that x is on the vertical axis now and positive x points down. Okay, positive x points down, and positive, and y is the imaginary component, which is the horizontal of our coordinate system. Okay, and so here are the equations. Here are the equations written in the 2x2 matrix for the squaring of the matrices using x and y. So if you look at the Mandelbrot generating code I gave you, I'm pretty sure I didn't do it this way. I'm pretty sure that I just switched x and y, which also works. So you could put y here and x here, which also works. But when you do that, then you end up with a left-handed coordinate system. And so I don't want to do that. All I want to do is rotate the axes so that positive x points down and positive y points to the right. And then all my code doesn't have to change. I don't have to invert the idea of x and y. I just have to remember that my x now points up and down and my y points left and right, but the entries in the matrix do not change. Okay, so in future code that I give you, this is going to be my coordinate system. There's one software I gave you where I had a little axis in the middle, and the axis has like a red circle is the origin, positive y is the dark blue, and positive x is the light aqua color, and green is the z-axis pointing towards me. So in the code I gave you previously, this was rotated counterclockwise so that positive x was here and positive y is here. So in future code, I'm going to just rotate the coordinate system. Basically, I'm rotating the camera counterclockwise by 90 degrees. I'm multiplying the camera by I. So I'm basically multiplying the camera orientation by, or rotation by I. I'm rolling it counterclockwise 90 degrees, which makes it look like y, positive y is to the right and positive x is pointing down. Okay. So that is my coordinate system that I'm going to be using. This is going to be the convention that I use in the future, and this is going to be the convention that I use when the aliens come to me and ask me to explain my convention to them. Okay, so that's it. I'm going to leave it at that. I think we covered a lot of ground here. Basically, what I want to do is I want to take a blackboard full of crazy equations and I want to erase it, and I want to put this onto the blackboard and say this is the creation process. This is the math that God might use to create the universe. Okay, this is a creation process that I'm looking for. My journey is to understand how the universe was created. Okay, what math can I use to demonstrate the creation process of the universe?